So we're going to talk about statistical inference, and there are two typical types of inference that we do. Okay, one is estimation. So while you're studying this material, you see confidence interval estimate for mean, for proportion, right? These are called statistical estimation. And then hypothesis testing, test of statistical hypothesis, right? So you probably review t-test, right? That's actually is about hypothesis testing. So when you do statistical inference, these are two typical things that people do, right? Either estimating certain characteristic or parameter of a population or of a distribution, or have a question related to this characteristic or a parameter of a distribution. You want to test that research question or hypothesis, right? So we're going to start from estimation, okay? And today we actually want to look at univariate situation. You know what univariate is, right? So you have just one variable, right, or one population, and you like to study certain characteristic or parameter for this particular population or certain distribution. For instance, what I have here in the picture here is a bell-shaped curve, right? And it represents a weight distribution. So weight, this weight could be any kinds of weight, right? Weight for male, weight for female subject, weights for maybe a certain species of animal, whatever, okay? And oftentimes the distribution shape for weights, right, look like a bell shape, right? But it could be non-bell shape, right? But regardless, oftentimes we're interested in a particular typical measure from any distribution, right? If it's quantitative, numeric, right? That is the mean of a distribution. It helps us know the location of this distribution, right? And sometimes, of course, we're also interested in seeing the spread, understand the spread, right? So that's sigma. What happened? Okay. What is that? Okay. Anyway, right? So sometimes you may be interested in understanding these measurements, right? The standard of the distribution of spread of a distribution, right? So estimating these parameters, right, is what we're going to focus on first, and we're going to look at estimating mean of its distribution specifically. Okay, so this is for numeric distribution. Now, sometimes you may be dealing with categorical variable, all right, or population of interest is of categorical type, like you're interested in the percentage of people who smoke or not. Right, so we'd be estimating a parameter p, right? Sometimes use p, sometimes people use pi, denote the percentage of people who smoke, right? Or nowadays you're probably interested in percentage of people who prefer a certain candidate, right, in the presidential election. Okay, so that's yes or no. It's kind of categorical type of variable, and oftentimes you're interested in estimating percent of yes, right? So that's an estimation, right? And we can do confidence interval estimate for that. And so for these estimation, for instance, I mentioned the parameter mu, which is the mean of a quantitative, a distribution of a quantitative variable, okay? The typical measure that we will use for estimating the mean, right? Mu is actually the symbol we use for population mean, if you recall, right? And the best number that we can use from our sample data, right, to estimate the mean of a population will be sample mean. We use X bar as a notation. I think you should now familiar with this, right? So we call this sample mean an estimator for estimating the parameter mu, the mean of a population, right? So I'd like you to know these notation because later on in the class, when you're reviewing that, these are the standard notation that we use, okay? So sample mean is an estimator for estimating the mean of a population. We also call the sample mean a statistic. Okay, this is the terminology people use. Sample mean is a statistic. A descriptive measure from a sample, we call it statistic, right? This mu, descriptive measure of a population, we call that parameter, right? So I think you have gone through this, right? So it won't hurt to review that again. So for estimating mean of population, we like to use sample mean, right? Now, variance of a population is sometimes also an important measure, right, parameter for describing a population, a distribution of a population. And a good estimate for that is sample variance, right? Population variance sigma squared. Sample variance notation is S squared. So S squared is a statistics that we use, right, for inferring the population variance. Okay, and it's also an estimator, right? We use that for estimating the population variance. And for categorical data, we have a so-called sample proportion. Usually, most of the book use a p hat, right, to denote the sample proportion. Right? That is the actual proportion data you get from sample. And you use that for estimating the population proportion. So today, we're going to review how to use a sample mean for estimating the population parameter mu, right, population mean. Also, the sample proportion for estimating the population proportion, okay, in estimation. Okay. And today, if we have time, we're going to also go over testing hypothesis for mean, right? And we won't have time for proportion, but we will do that later on, right? So while you're doing this estimation, you will take a random sample, hopefully representative random sample, okay, and try to use the information you get from the sample for estimating the parameter of a distribution. For instance, you want to estimate population mean, you use a sample mean, right? So it's just a random sample from that population. And you know that every time if you take a random sample, right, you take twice, you take 3 times, for instance, if you're allowed to do that, these measures are going to be different, right? There is that sampling variability. So in order to do a proper job for statistical inference, for estimating population mean using sample mean, we got to know the variability pattern, right, or distribution probably model, right, that help us understand the variability pattern of the sample mean. So we can properly use this statistic for estimating the parameter of a distribution, the mean of a distribution, right? So that probability model for the statistic, sample mean, for instance, we call it sampling distribution. So it's a probability distribution. Help us understand the variability pattern, right, for this sample mean. Right? So we're talking about a distribution. Sampling distribution is a distribution, right? So for inference, for estimating population mean, we like to use a sample mean. And what's the probability model for that sample mean? Or what's the sampling distribution of that sample mean? Of course, it's the distribution, so it has a shape, okay? You learn so far different distribution like binomial, Poisson. It all have different shape when you have different parameter value, right? And normal distribution is one of the distribution that has a bell shape, okay? And it's a shape, right? Then we need to know what kind of shape it is for this probability model. Okay, so in fact, the sampling distribution of the sample mean has a bell shape under certain condition, which is really great because we know a lot about this normal distribution, and you just review it, right, in the last chapter, right? So we actually, from a couple of theorems, we get that the distribution of sample mean, right, actually can be normal under certain condition. And also, we also want to know some important parameter help us to have a complete information about this normal distribution or the sampling distribution. So we need to know the mean and standard deviation for this normal distribution so that we really know what's the sampling distribution for the mean, okay? Now, there are these theorems, right, actually in the note that talk about that, right? First theorem is that if you take a random sample of a size n, right? This n could be 15, could be 100, whatever, right? If you take a random sample of size n from a population, and this population has a mean mu and standard deviation sigma, if these information is known, right? Then the sampling distribution of the mean will have a distribution that has a mean that's the same as the mean you try to estimate, right? That population mean, right? And the standard deviation for the sampling distribution of mean or probability distribution for sample mean will be standard deviation of the population, right, divided by square root of sample size. So this is a known theorem, right? This helps us understand the parameter of the population and parameter of the sampling distribution of the mean. So the mean of the sampling distribution is the mean of a population that your sample is from, right? The standard deviation from the sampling distribution is standard deviation population divided by square root n. And sometimes we call this thing standard error, right? Which is the standard deviation for the probability model of probability distribution for sample mean. Okay, this is an important result, okay? And the statistician, mathematician derive that result, so we just take that, right, and use it in practice. So that was about parameter for that sampling distribution. Now, what about the shape of the sampling distribution? These two theorems actually help us know the shape of the sampling distribution. Theorem 1 says if you if your sample is from normally distributed population, right, then the distribution of a sample mean will be normal. So that's great, right? If your weight is normally distributed, and if you want to study understand the sample mean of weight, right, distribution of sample mean of weight, right, is actually also normal distribution based on this theorem. Now, sometimes you may have a population or a distribution that is not bell-shaped, not normal. Here, the second theorem actually help you to reach a distribution shape of the sampling distribution. That is, if you have a relatively large random sample, taking from any distribution, it doesn't matter, right? This sampling distribution, the mean will be approximately normal too, right? So if the population doesn't have a bell-shaped distribution, doesn't matter. You raise your sample size to a certain level, the probability distribution of the sample mean will also be normal. So that's great, right? If either one of these conditions satisfy, we would know the distribution shape of the sample mean, okay, and which is normal. And we know the distribution, normal distribution, very well now, right? So we actually know the probability distribution for the sample mean very well. So this is kind of like a graph showing the sampling distribution of the mean or probability distribution of the sample mean. If the population is normal, right, or if you have relatively large random sample, the sample mean, this statistic, its probability model will be bell-shaped normal, okay? And the mean of that distribution will be equal to the population mean, right? The mean of a population where your sample is from. Of course, in practice, you never know this mean, okay? And this is the number you wish to estimate in the future, okay? And it also says the standard deviation, right? Sigma over square root n is a standard deviation for the sampling distribution of the mean. Again, the sigma is unknown, okay? But if sigma is known, then sigma over square root n, the standard deviation of population divided by square root sample size, will be the standard deviation for this probability model of sample mean, right? So these are important theorems that help us to understand the variability pattern, or model the variability pattern for the sample mean that we wish to use for estimating population mean. I hope this makes sense. So you've been studying this, so I hope these few slides actually help you to get the idea. So if you understand that distribution of a sample mean is bell-shaped under those conditions, okay, of course there's possibility that, your population is not normal, your sample size not big enough, right? If that's a condition, then the distribution of the sample mean would not be normal. Then we have to look at other alternatives, right? So today's lecture only for those situations that your population is normal or you have a relatively large random sample, right? We have some procedures that develop based on normality results or normal distributed sampling distribution, right? So we can use that to actually form confidence interval and also do hypothesis testing. So we're going to start with confidence interval first, okay? So after you study all these material, I think you probably realize that there's one important formula for estimating mean of a distribution, right? And that is this formula I shown you here on the slide, okay? That formula based on the point estimate, which is the sample mean. So when you take a sample and find the average of that sample, that's this number here, okay? So the confidence interval actually is this, your sample mean, this point estimate, right? Plus or minus, this term here is called margin of error, right? The margin of error is actually this particular t-score times this is the estimated standard error, okay? Now, you know what that standard error is, right? Standard error is what? The standard deviation for the distribution of the sample mean, okay? And that t-score actually is some kind of z-score too. It's a standardized score, okay? This actually helps us to determine how large margin of error is, right? In terms of number of standard error or standard deviation from the sampling distribution of the mean, okay? And how large this t-score or standard score is, it depends on how confident you want this interval to be in estimating a parameter. Okay, we use a number called confidence level. Okay, and usually people use 95% as a confidence level, right? So if you use 95%, then this particular t-score that you calculate will be based on that 95% confidence level, right? So in order to do the confidence interval estimation, this is what you do. Just apply this formula. Find the sample mean here. You know the standard deviation from the sample. You know the sample size. and then just use the confidence level you have to figure out this particular standard score, and you're done, right? Your interval will be sample mean plus or minus this marginal error. If you use the sample mean minus this marginal error, you get the left end point of the interval. If you add this point, add this value to the sample mean, you get the right end point of the interval. So you're going to have an interval for estimating the mean. And this is the formula everybody uses, right? While you're studying, you find out that there's places that they talk about Z-score, okay? But Z-score is not the practical one, okay? And I'm going to explain that to you, okay? So, so remember, this is the formula you will use when you do homework, right? Or when you run our software, SPSS software, when they produce some confidence interval estimate for mean, this is the formula they use, okay? Keep this in mind, right? Okay, so I'm going to quickly talk about the concept behind this, so it'll make more sense to you why a formula look like this, okay? So when you try to estimate the mean of a population, you will start with using a sample mean, right? This is we call it point estimate, a value on the real number line that you use for estimating the mean of a distribution, okay? So you calculate this based on the sample you get. It's pretty much just the average from a sample, okay? Now, in reality, there's really a true mean of a distribution. We never know that, right? But there's actually a true mean, okay? The difference between the true mean and the actual sample mean you got, right, is the error that you made, right, in estimating the true mean, right? But you never know true mean. We are trying our best, right, to actually get an idea where this true mean lies. That's what this confidence interval is about, okay? So what is the confidence interval? For estimating mean, it's actually based on the sample mean, okay? You actually define an interval. Make that interval center at mean, the sample mean that you get. And this is how the confidence interval look like, right? Is that sample mean you get plus or minus, we call it margin of error. So if you add your sample mean, add that margin of error, you get right end point. Sample mean minus the margin of error, you get the left end point, okay? That's what the confidence interval look like, the regular confidence interval look like for estimating mean. Although in Pagano's book, you probably see one-sided confidence interval. Sometimes people do that, but most of the time when people report in confidence interval, they'll report it in this form, right? Sample mean plus or minus margin of error as a confidence interval estimate for mean. So how you decide on this margin of error? There's so-called a confidence level, right, that we use to decide this margin of error. The confidence level is large, this interval will be large, okay? So what I show here is, if in case you want to estimate maybe the average body temperature, right, you may get a result like this, 98 plus minus 1. That means what? The mean body temperature is probably from 97 to 99. This is the result you report, all right, using an interval. Okay, but we're going to talk about this interval and look at some application. So I'm going to first talk about how we construct, how we define this confidence, how people made up this confidence interval. Okay, we mentioned that the distribution of a sample mean is bell-shaped under some condition, right? Either the population is normally distributed, or you have a relatively large random sample, right? Then the distribution of the sample mean will be bell-shaped. And that sample mean distribution has a standard deviation. Okay, remember the standard deviation, actually standard deviation of the population divided by square root n. Okay. And we're going to use this, when we construct confidence interval, we actually make use of this distribution of the sample mean to decide the size of this confidence interval. Okay? And oftentimes people do 95%. So what 95% means? That means I'm going to find an interval centered at the mean of this distribution of sample mean. That will cover center 95% of a distribution. Okay? Then once I found that, that will be the size of the confidence interval. So the size of the confidence interval is actually from the sampling distribution of the mean. Okay? So what will be the size of this confidence interval if you do a 95% confidence interval? Well, first thing I will need to do is figure out Z-score for this, right? You know that for normal distribution, it's really how many standard deviation are these points away from the mean. That matters, okay? So if I know how many standard deviation are these two endpoints away from the mean of a distribution, I'm almost done because that number, that's a z-score. That z-score times the standard error. This is the actually margin of error. Twice of that is actually the size of this interval, which is actually the size of the confidence interval, right? So I want this slide just help you to understand how we determine the size of the confidence interval. And you know what will be the z-score for this. If you use a standard normal table, right? If you want to find a z-score for this point actually is at the has a cumulative distribution of 0.975, right? Because its right tail is 0.025. So this point has a z-score 1.96 because its cumulative distribution is 0.975, right? How did I say that? Because you can look up a table for it, right? Let me quickly, just quick review. I think you did this before, right? So look at the Elmo. Let's see. You come to this table. This is actually a book from Pagano's book, right? And Pagano's book, it has a normal distribution table that gives you right tail area, okay, and a z-score. So for a z-score that is left tail is 0.975, right tail is 0.025. So you look for 0.025. Where is it? 0.025. It's over here, okay? 0.025 has a z-score 1.96. Right, this 0.025, again, is right tail area. Right? So that gives us 1.96. So if we go back to this slide here, this z-score here will be 1.96. Right? Of course, this is to the left of mean, so this is 1.96 again with a negative, right? That means you're going to use mean, subtract 1.96 standard error. You get the left endpoint, right? Again, we never know the mean of a distribution. Would that matter? No, because determining the margin of error, we just need how many z-score it is, right? So that z-score you found times the standard error, you get the margin of error. Now, if I need 95%, of course, it's 1.96, right? If I need like a 98%, okay, then it'll be different. Then I want to have a z-score found here, right? That it's right tail. If it's 98, the cumulative distribution at this is 99.99, and right tail will be 0.1, right? So I will look up at standard normal table, look for z-score that is 0.1. So actually 0.1, do I have a 0.1? Actually, I do have a 0.1 here. I have several 0.1 here, okay? So usually if you have several 0.1, I'm going to find a midpoint here, okay? So it'd be 2.3. Actually, it's between 3 and 4. So you can say 2.3 or 2.4. I mean, actually 2.33, right? Or 2.34, or in between the two, if you like to, right? It really doesn't matter, right? The difference is not so big. So if you change the confidence level, you just change that, right? Change that z-score. You get the margin of error. Right, so it's almost done, right? The confidence interval estimate is what? Your sample mean, sample mean plus or minus margin error. So you're done, okay? This is if you are using a z-score, standard normal table to do this, okay? So here I have a picture actually showing the special notation z of some subscript, right? So if you're doing 95%, we have the notation for this. This z-score here is z of 0.025. Z-score of a subscript stands for z-score that its right tail area is that subscript. Right? That's actually a notation that the author of the Pagano's use, right? The z-score subscript notation. It stands for z-score such as its right tail area, right, is that subscript. Now, if you read other textbooks, you may see people using cumulative distribution as a subscript, or left tail cumulative distribution as a subscript, okay, here. But Pagano's book is using right tail, and his textbook also uses the right tail for standard normal table, okay. So I just like you to know, in case sometime you read a z-score, and then the subscript actually stands for cumulative distribution, that doesn't mean that Pagano is wrong. It's just people have different way of doing things, okay. So our book, right, in our class, notation stays the same. We have a z of some subscript, all right, that stands for a z-score that such as right tail area is that subscript, okay. So in order to construct a 95% confidence interval, of course, first thing we would like to do is figure out the z-score right? That would cover standard 95% of the distribution. Okay, so this helps us decide the size of the interval. That is what? 1.96 times standard error, right? This is sigma over square n. If you know the standard deviation population divided by square size, the square root of sample size, you get that. So that tells us also another thing. That is, if I randomly pick a sample and calculate the sample mean, the chance that sample mean lies in this range is what? 95%, because this is a distribution of the sample mean, right? So let's say I take a sample, and that sample mean lies here. Now, 95% chance, or I say the sample mean lies in that range. So this happened to be one of those. Then what is actually the confidence interval estimate that we report? Well, that confidence interval estimate actually is an interval centered at this point estimate, but the size of the interval is actually this one, right? We say that we have determined the size, right? That's using the 95%, right? So we just shift that interval, make it centered at the sample mean. That gives us the confidence interval estimate. Right? So in practice, when you are estimating mean of distribution using confidence interval, that's an interval you get. Okay? Now, there's a possibility that you get a sample mean over here to the left, sometime to the right, sometime very close to the center, but there is 5% chance that this value actually lies on this left tail, right tail, or left tail. When those point estimate lies in this right tail or left tail, if you try to put an interval like this, make it center at that point estimate, your interval won't cover the true mean. Okay? Only those intervals when you have sample mean lies in this range, right? This 95% range. And if you put a same interval centered at that, those intervals cover the true mean. Again, this true mean we don't know, right? We do not know this true mean. But this interval kind of gives us an idea, right? If the true mean exists is over here, and you happen to get a point that is within that 95%, then this interval covers that true mean. So this is telling us while you're really doing a confidence interval estimate, right, in practice, there is a possibility that you get a sample point that's so far away from the actual center, actual mean that you try to estimate. So your interval is not correct. There's a chance for that, right? In this case, what's the chance for that? 5% chance, okay? You have 95% chance that this interval covers the true mean, but there's 5% chance that this interval doesn't cover the true mean. Okay, hope that makes sense to you, right? So this is actually the confidence interval estimate, right, when we do 95% confident. Okay, so here is like an example showing you if I'm able to actually keep randomly take sample one at a time. I took one sample, I got this interval like this. Take another sample, it could be here. Next could be here, and it'll fluctuate around, right? Every time you take a sample, find a mean. But 1 out of 20 times, you could have a sample mean that is just far away from the center. And so when you construct an interval, that interval doesn't cover the real mean that you try to estimate, right? So you always need to know that when you do statistic, there's always some uncertainty, right? But here, we construct this confidence interval using 95%. So that's pretty high level already, right? If you like to, you can actually create a 98% or 98%, right? But I'm sure that you don't want to do 100%, because if you do 100%, what will be the size of the interval? In negative infinity to positive infinity, right? So interval will be too large. There's no sense now, right? So 95 is actually very commonly used confidence level, right? If you do increase your confidence level, you do know what's going to happen to this interval. You're going to increase the size of the interval, right? Sometimes the size of the interval is too large, it just doesn't make sense to you to actually explain that to you, to people, what's the mean of a population. Okay, so hope that makes sense to you. So from these slides, we actually come up with an interval estimate like this: sample mean plus or minus some z-score times standard error. And this is assuming that we know the standard deviation, okay? We know the standard deviation, so this particular structure that we just went through, it works. Okay. However, in practice, you never know the standard deviation of a population. If you know the standard deviation of a population, you should know the mean of a population too. There's no sense to do estimation, right? It is sometimes that people think that they really have good idea, right? Like where that standard deviation lies based on their past experience, so that they use this, right? Otherwise, really nobody uses this formula. Okay, so what is a more practical formula, right? Sometimes people say, how about I increase the sample size? Make a sample size so large. When sample size is large and you do have a random sample, okay, then the sample standard deviation will be a good estimate for this population standard deviation. So in that case, we can use this formula again, but replace this by standard deviation of a sample. Okay, that makes sense. All right. But when sample size is small, you know, if I use a sample standard deviation here, when the sample size is small, you realize how terrible, right, the information you will get about the population when you have a small sample. Right? Remember, I kind of show you some small sample and try to see the normality from small sample. You don't see the normality. Okay, so there's large sampling variability there. If you try to estimate the standard deviation of a population using sample standard deviation when sample size is small, it has large possibility of committing large sampling error. So a person, very famous person in statistics, right? William Gossett, years ago, in 2 centuries ago, well, within 2 centuries, I think, right? Long time ago, more than 100 years ago. Let me think, I can't even remember how long it is. But anyway, he found out that there's serious error when you have small sample involved. Right, so it's better not using this formula when you have small sample, right? So what he found out is actually also later on another famous statistician, Fisher, right? Later on you're going to learn Fisher exact test, that same Fisher, right, who actually derived a distribution for this t distribution that is good to use for adjusting the z-score so that we can feel safe using the estimate for standard deviation using sample standard deviation, right? So here is the formula that I shown you earlier today, right, about confidence interval. I said that's more practical formula and everybody use. That's this one, okay? Instead of having z-score here, we actually use a t-score, okay? Now, the reason we can use z-score because we know the standard deviation. So if we try to standardize a normal distribution, especially for sample mean, using the accurate standard deviation of population, standardizing result, the standard score follows standard normal distribution. However, if you use the estimate for standard deviation when sample size is small, that z-score no longer follows standard normal distribution anymore. It actually follows a t distribution. Okay, so we've got to adjust this formula. We've got to adjust this formula, right? And the adjustment is made on this standard score. Or now it's called t-score now, right? And so t-score is actually, like I said, all right, when you try to standardize sample mean, and this is normally distributed sample mean, right, using the estimate for standard deviation, this quantity follows a t distribution. And sample size small, when sample size small, this t distribution will have larger spread, right? When sample size gets larger and larger, this t distribution actually gets closer and closer to standard normal distribution. So t distribution is very similar to the behavior of t distribution, very similar to standard normal distribution. Okay, and this t distribution related to sample size. Actually, it has a parameter called degrees of freedom, which is the sample size minus 1. And when sample size get larger and larger, this t distribution again, like I said, get closer and closer to standard normal distribution. So that means this formula will get closer and closer to a formula that has a z-score that we have there, right? When we have large sample. Okay, so in our textbook, they say, well, if you have large sample, I just stay with this book, right? I mean, this formula, and just replace the sigma by s, right? That's okay, right? But still not as good as using this formula. This one is more conservative. Okay, it tends to give you a larger interval, which means you will have the confidence level that you specify for estimating the mean of a distribution. Okay, so the only difference between this formula and the one with the z-score is finding out this t-score, and there's a t-table for it, right? So once the confidence level is given based on that confidence level and the sample size, which give you the degrees of freedom for that t-distribution, you can figure out this t-score. Okay, let's show. So this is one version of t-score table. This is from Pagano's book. Once you have the degrees of freedom, if you know the confidence level, it actually table gives you the upper tail or right tail area. So if you have a 95% confidence interval, you need the right tail 0.025, right? So if I'm trying to find a 90% confidence interval here, for instance, when that sample size, my sample size is 3, then degrees of freedom is 2. So I will look at degrees of freedom of 2, and then since it's 90%, so right there is 0.05, so I got the t-score for that, right? So in case you want to do a 90% confidence interval, when sample size 3, the t-score you use will be 2.92, right? If you want to do 95%, then you should look at the right tail 0.025, and your t-score will be 4.30. Okay, so this is how you use this t-table. And of course, if you use a table provided by Pagano, not Paganos, but the ebook and the WebAssign, right? It actually has a setup table for you too. You can use that, right? That one actually is pretty handy. In fact, they give you confidence level, and then you get the, you don't have to divide by 2 to try to figure out tail area. Let me show you this one. Right? In that book, if you know your confidence level, you know your degrees of freedom, your t-score is right there, just right under that column. Right? So that's pretty neat, right? So save you some trouble, try to draw a picture and try to figure out whether you should actually divide by 2 or whatever, right? So that's another option, okay, that you can use. So either table, right? And of course, if you have software just do that for you automatically, right? You have Excel, you have R that can do that automatically for you. So actually, this is the one that from the ebook, right? Okay. So if we look at this example, I took a random sample of size 10, and sample mean is 80, standard deviation 18.5. All right, this is taken from a population of female 10 years old, right? And if we assume that this is about estimating weight for these type of population, if the weight is normally distributed, right? Again, that's an important assumption, right? Because this is a small sample. If weight is normally distributed, that's actually an assumption behind this particular formula. If you look at this formula, assumption for this formula is that population must be normally distributed, right? And you're estimating standard deviation using a sample standard deviation. Okay, so, and this particular procedure is good for sample size small. Most of the textbooks say 30 is a small sample, okay? But it really depends, right? Some of the distribution that is very skewed, 30 may not be a good number for you to decide large or small sample, right, for normality conclusion for sample mean. Okay, so, but you know, in practice, actually nobody care about that, either large or small. Everybody use this formula. However, in case your sample is really small, you got to check whether the population is normal or not. So you want to check for normality. But you do realize, right, when you do normality check, when sample size is small, most of the time you pass the normality, right? So you really have no clue where the population, what the population distribute. I mean, the sample mean could be approximately normal or not, right? Anyway, everybody actually just regardless, small sample and large sample, right? But for the class purpose, when you're doing this and I give you a test question or assignment, when you see a small sample, I like you to really just verify normality, right? Because that's the assumption behind this. And that's a good habit. Anytime you use any statistical procedure, right? To be able to use it properly, you got to always check the assumption behind it, especially distribution assumption, because that's how this whole formula is derived, right? Remember, I've shown you step by step, right, from the graphs, right? See how people develop this confidence interval, right? It's actually based on normality, okay? Especially small sample size, you want to check on that, right? Okay, so for this particular problem, okay, we first calculate the mean. I missed a bar there, right? Mean 80, standard deviation 18.5. And if I want to do a 90% confidence interval, right, I got to look for T of 0.025, or just use a Web of Science textbook, use a 95% as a confidence level. And degrees of freedom, since sample size 10, so degrees of freedom is 9. I look up a table, the t-score is 2.262, right? If you use a Pagano's book, 95% degrees of freedom is 9. Pagano's book give you 2.26. Right? Some book give you one more decimal place. All right, some give you less. And for you, when you do WebAssign, I do recommend you to actually either use R or use Excel to give you more accurate number, right? And that's what you do in practice too, right? If you have a software, you want to use a software to give you more accurate number, okay? So for this problem, you got that t-score, and that's the most important one. Once you got that, you have the mean and standard deviation. Remember, this should be an X bar. I don't know whether it has an X bar on your node or not. Right? So what you do is plug in 80 for the X bar, t-score 2.262, and standard deviation over square n. And this part here will be your margin of error. Right? That is 12.91. That's a margin of error. So you use your mean, subtract margin of error, you get the left endpoint. Mean plus margin of error, you get the right endpoint. And that's your confidence interval. You're done. Right? This is for estimating mean of a distribution. Okay? And remember, smaller number on the left, larger number on the right. That's how you present an interval. Okay? A lot of time I see students actually have these two numbers in the reverse order. That's incorrect math expression for interval. Right? So smaller number on the left, larger number on the right. Okay? Cool. And this is actually... I ran the R-Commander, checked for normality. I got a p-value of 0.4517. I guess you know how to conclude this, right? If a p-value larger than 0.05, you're going to say, well, I can accept normality, okay? So I'm good to use that formula because the sample size is small, right? Then R-Commander has a one sample t-test option, okay? You can actually do a t-test, but let's not worry about it. There's a 95% confidence interval estimate there, and this is the same as what we got there, right? So if you use R-Commander, once you have data entered, just click one sample t-test, choose one sample t-test, they will give you this number. They give you the mean, of course, okay? This is the view with R, okay? I was thinking of asking you to measure your pulse rate and see if we can generate the data, right? I think let's just skip that, right? We probably don't have much time, okay? But here is just kind of a review what we did, okay? We learned this formula here earlier, actually to understand the idea how we construct the confidence interval. But when sample size is large, I said, well, we can replace this by sample standard deviation. When sample size is large, this is also a reasonable one, right? But in practice, this is the one that everybody uses. When you run the statistical software, this is everybody reporting, right? So make sure you know this one. Whether you know these two, don't really mind, right? But this one is the one that you really want to know, okay? It says 1 minus alpha. I just tried to give you this alpha notation there. But you don't have to stay with this. As long as you know the concept, it's 95%, right? Then this t-score is t-score for constructing 95%. You go to the web, assign ebook, look for 95% column, give it the right degrees of freedom, which is sample size minus 1. You get this t-score, correct t-score there. Right? Okay. It's good to know it, but you have the software. Software can take care of that for you very quickly. Okay. But in the WebAssign, actually, there are some questions probably I ask you to do that, right? Check table or use the software to do it, right? You just have to practice this, right? To really get a good sense what it is, right? Sometimes you keep using the software and you probably forget what's the meaning of the confidence interval. That's not good, right? When you're reporting it, you want to know exactly what you're doing, okay? And also, there is a sample size issue there. Okay, you know that this is a formula for confidence interval estimation, and this part here is a margin of error. If I still use a z-score there, this is a margin of error. Okay, now this margin of error actually the size of it will be affected by confidence level. You know that when we use large confidence level, we're going to have a larger t-score or z-score, right? So margin of error will be large. Also, it'll be affected by sample size. When sample size is large, of course, this number is a fixed number when you decide the confidence level. Standard deviation for a particular population is also a fixed number, right? So if you increase the sample size, that would decrease the margin of error. Right? When you're reporting estimating let's say here is the mean weight, okay? I say from 67 to 92. That's a big range, right? When you try to get a good sense what's the average weight, you like this interval to be smaller. This interval actually range almost 25. That's a pretty large interval, right? I want to reduce the interval. How do I reduce that? Increase the sample size to allow you to reduce that, right? So there's actually a formula for it, okay? This formula is based on the formula of marginal error. I just set the marginal error equal to this formula. Solve for n, I get this formula for sample size. This sample size will help us to achieve a goal in terms of marginal error. Here I use E. Some of the book use M, some of the book use B, right? But it doesn't matter, right? Just marginal error. So you know the confidence level, you know this. If you have some estimate for the standard deviation from the pilot study, for instance, right? Then you can put in this information. And then if you have specific goal in terms of marginal error, you can put it in there. Then to help you to get the sample size. For instance, let's look at this example, right? If you plan to survey a resident in your county to find average health insurance premium that they're paying, and you want to do a 95% confidence interval for estimating the average premium that they pay, and you want the marginal error to be within $50, right? Try to estimate the average premium that they pay. Okay, so that's assuming that people have done some pilot study, right, and get an estimate for the standard deviation of the premium pay, insurance premium pay for people living in this place, and that's 400. So in this case, standard deviation information is provided. It's an estimate. Okay, so what sample size should you use so that you can get a marginal error with a confidence interval estimate with a marginal error of $50? Right. This is based on 95% confidence. Okay, so I can just apply that formula. 95%, right? That means we're going to use a Z-score for 95%, which is 1.96, right? Sigma was provided from pilot study. That's 400. Just plug in 400 for sigma. I want my marginal error here. I use B, right? It can be E, right? It's marginal error, and that is 50. So if you have a node, I probably can change this to E. Just be consistent with the E that we have earlier. Okay. So this is marginal error. Just plug them in. You get a number 245.86, right? Of course, you don't have a fraction of a subject, right? So usually we run up to next higher integer. You know, the larger the sample, the better the estimation, right? So always run up in this case. So this tells you that if you want to do confidence interval estimate for average premium in that community with marginal error within 50, you need a sample size 246 to help you to achieve that goal. So you can do that. You don't want to actually go out, get the data, come back and see, well, marginal error is too big. I'm going to make another trip, come back, still not enough, go and keep going. You're wasting your time, right? And actually, while you're doing this, you have different time points to do the estimation, so there are bias involved in there too. Okay, so make sure that you can just make one trip, right, and you can get everything back and get a confidence interval with marginal error that meets your requirement. Okay, good. So that's about estimating mean of a distribution. Okay, I spent, I think, 1 hour, right? 1 hour. I hope you get a good grasp about